Hello, my name is Vyacheslav Siniy, and I will present our work titled In Context Reinforcement Learning for Variable Action Spaces, developed in collaboration with T-Bank, Dunalab, and IRI. Our research focuses on in-context reinforcement learning, a subfield of meta-reinforcement learning that aims to create agents capable of generalizing across the four components of reinforcement learning environments. Previously, in-context reinforcement learning couldn't generalize across different action spaces. This capability is crucial for applications in recommender systems, agent-based models, and the development of foundational decision-making models, which require handling diverse action spaces during large-scale pre-training. We define the types of new action sets as follows. First, there are actions the agent trains on. If the size of a new action set doesn't change, let the new actions be either permutations of the training actions or entirely new actions. If the size does change, the new action set may include additional new actions or be a mixture of seen and unseen actions. As a basis for our approach, we used a model from previous work on in-context reinforcement learning called algorithm distillation, which demonstrated the generalization on novel tasks with changing reward distributions. It is a transformer-based model that takes the current state and the history of previous interactions with the environment as an input, and outputs a distribution over actions. However, when applied in the setting of changing action sets, this model exhibits a significant drop in performance when the size of the action set remains the same, and becomes completely unable to process new actions when the size of the action set changes. In our paper, we introduce an improved approach called headless ID that maintains high performance when unseen actions are introduced, and even when the action space increases by a factor of 5 compared to the largest action set seen during training. We achieved this by identifying and removing all parts of the model where the weights are tied to the action space. In other words, we transitioned from in-weights learning to in-context learning for handling actions. First, we noted that the ID architecture has a linear layer at its output that maps action representations into a probability distribution over actions. Since this layer's size is predefined and its weights are learned, it cannot adapt to new action sets post-training. We removed this layer and manually calculated the probability distribution by comparing the produced hidden state with a collection of action embeddings that are not trained and can be defined as new actions appear. During training, we use contrastive loss instead of cross-entropy. Second, we remove the embedding layer at the network's input. This layer maps action indices into embeddings and is trainable, preventing the addition of new actions post-training. Instead, we encoded actions using random orthonormal vectors. When a new action appears, we simply add a new random vector to the collection of embeddings. Lastly, since we removed all information about the action space structure from the model, we returned it by including random action embeddings in the input context. And though they don't contain any semantic information about actions, we expect the model to infer the meaning of actions from the context by observing their effects on the environment. Here is a visualization of headless ID architecture. We validated our approach in 3 environments, demonstrating the high generalization abilities of headless ID. First, we tested on multi-armed bandit using the regret metric. We compared ID in headless ID against the Thompson sampling, a bandit-specific algorithm known for fast conversion to the optimal action. Despite the number of arms being larger than those used during training, headless ID showed high generalization, closely matching Thompson's performance. In contrast, ID required retraining for each new action set and showed degraded performance with large action set sizes. We observed similar behavior in the contextual bandit environment, where headless ID maintained its performance even with a 5-fold increase in action set size during evaluation. And, unlike ID, it did not require retraining. Finally, we saw the same levels of generalization in the darkroom environment, where headless ID maintained its initial performance across all new action spaces. For more details, see our paper and the published code at the provided links. Thank you.